All right, so in this module, we're going to talk about the way that polymers are created, or polymerization. And so to start with that, I want to kind of address some nomenclature about hydrocarbons, which are often the monomers to polymers. So if we have unsaturated um, hydrocarbons, those are hydrocarbons that have double and triple bonds. And so what I mean by that is if we look at this, we see carbon-carbon double bond with hydrogens. And so that double bond, that's found in this ethylene or ethane. And then we have this triple bond down here with hydrogens filling out. So C2H4 up here, C2H2. Both of these are classified as hydrocarbons, and both of them have either a double or triple bond. And so that means that it's unsaturated. On the other hand, a saturated hydrocarbon is one in which all of those bonds, all the carbons, are singly bonded to other atoms. And so here, methane, the simplest one we can think of, is singly bonded to 4 hydrogens. And then ethane here is singly bonded to carbon, but also the other hydrogens. So that's the kind of the difference between those. And the reason I mention this is that it kind of goes into the monomer and how that forms some type of polymer. If we think about ethylene, which has a double bond, and so therefore is unsaturated, we also have phenol here, which you can see from these dashed double lines here. Those are double bonds. Both of these can effectively break those bonds to form some type of repeat structure in a polymer. So here with ethylene, if we break the carbon double bond to form a single bond, that can free up bonds on either side. And so this looks an awfully lot like the repeat unit of polyethylene. And so that's actually how we get polyethylene, is by breaking the double bond in this case. And so when we can form 2 new bonds from this, we call it bifunctional. So basically, functionality is the number of bonds a monomer can form. So ethylene is bifunctional because it can form 2 bonds here on the ends. And so when ethylene is used to form polyethylene, it forms another unit cell or repeat unit on this side, and that's what continues to form the chain structure. Phenol, on the other hand, has double bonds here, here, and here, and each one of those can be broken to form a new bond, as you can kind of see over here. So you can see a CH2 group, CH2 group, CH2 group. And so this is known as trifunctional because it can form 3 bonds from this monomer. So that's what we mean by functionality, and that kind of determines what type of structure. So this tends to grow into a linear form, a chain, whereas this one, which has 3 bonds, tends to form in more of a network-like structure. All right, so let's take a look at how polymers are synthesized for a second. And one of the most common ways is known as free radical polymerization. And speaking of polyethylene, let's look at how free radical polymerization is used to form polyethylene. So we start with the monomer, like I said, ethylene. It has a double bond, so it's bifunctional. And we have a free radical, here just represented by R with a little dot. And so a free radical is something that can interact with the monomer and break that bond, and in doing so, bond to the monomer. And so through that process, it breaks the double bond, and the free radical bonds to one of the carbons, and it leaves behind, because we know it's bifunctional, another site over here in which could be bonded to something else. So this is kind of known as initiation. So it initiates the formation of the polymer, and it has an unpaired electron or active site, just like this free radical did. So it basically initiates that and forms this active site for more bonding. And so then this initiated molecule can interact with another monomer and continue to grow. Because there's two of them involved, we call it a dimer, and that propagates the chain growth. And as you can kind of tell where this is going, it will continue to interact with more and more of these monomers to build up the chain here and build up the structure. And how long it does will affect the molecular weight, which we will talk about in another section. So that initiator, if you're kind of wondering what this R thing is up here, an example of that is the benzyl peroxide down here. And basically, this is a molecule that kind of gets broken up into two. It kind of gets cleaved here. And then each one of those is going to have an active site which can interact with the end. So basically, this thing would be at the end of each polyethylene chain. All right, so so what we just talked about is known as addition polymerization, and that's one of the two main synthesis routes for polymers. So addition polymerization, like I just said, or chain reaction, both of those are kind of the names that we go by, and it's basically what we're talking about here. That kind of process. And so this is useful for polyethylenes, for polypropylenes, PVC, polystyrene. So these are what's known as vinyl polymers, which means they have the carbon backbone. There's also the other main synthesis route is known as step reaction or condensation polymerization. And this is important for PET, polyesters, bakelites, nylons, and polycarbonates. And so this is kind of an example of that process very briefly down here where we have tetraphthalate acid, ethylene glycol, and those two bond and form this repeat structure that's repeated over. So basically, it's a step process because we have two parts. We have the tetraphthalate acid and the ethylene glycol. Both of those have to combine to form the repeat unit, which is then repeated over again. So it's not growing by addition like this one, where we can always add another a monomer to the end. This two separate distinct molecules have to bond together in this step process to get one of those repeat units that can then bond to another one, but that has to be bonded together. So it's basically a more two-part process. So these two have to mix together or bond together to form this that can then repeat together. So that's kind of in a nutshell what the step growth process is.